Let me show you how to be a good Bayesian.
Today, I'm excited to be joined by David Kohns, a postdoctoral researcher in the Bayesian workflow group under Professor Aki Vettari at Aalto University. With a background in econometrics and Bayesian time series modeling, David's work focuses on using state space models and principled prior elicitation to improve model reliability and decision making. In this episode, David demos live how to use the AR-R² prior, a flexible predictive prior definition for Bayesian autoregressions. We show how to use this prior to write your own Bayesian time series models, AR, MA, ARMA, autoregressive distributed lag, or ARDL, and vector autoregressive models, VAR. David also talks about the different ways one can generate samples from the prior to mimic the different expected time series behaviors, and look into what the prior implies on many other spaces than the natural parameter space of the AR coefficients. So you will see this episode is packed with technical advice and recommendations, and we even live demo the code for you, so you might wanna tune in on the YouTube channel for this episode. And if you like this new format, kind of a hybrid between a classic interview and a modeling webinar, well, let me know, and let me know which topics and guests you would like to have for this new format. This is Learning Bayesian Statistics, episode 134, recorded April 24, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com. David Kohns, welcome to Learning Bayesian Statistics.
Thank you very much. Pleasure to be here.
Yeah, that's great. I'm delighted to have you on. I feel I could do a live show at Aalto University and just interview everybody one after the other, and then have 1 year of content, and then just go to an island and only sip Mai Tai, and just earn passive income thanks to you guys.
I'm sure we can organize that.
Yeah, full disclosure, I would not be able to live with only the podcast. That would not work at all. It's not a good business model. Don't do that, people. But if you want to have fun, then yeah, do it. No, it's great to have you on. I'm going to have also Timu. I don't know if that's how you pronounce his name, but I'm going to have Timu on the show in a few weeks. Also, Osvaldo has been here. Aki, obviously, and I think Noah should come on the show one of these days to talk about everything he's doing. So Noah, yeah, I need to contact you. So, anyways, today's you, David. Thank you so much for taking the time. I've been reading your work for a few weeks now, because you're doing a lot of very interesting things about autoregressive models, state space models, how to choose priors, and so on. So that's really cool. We're going to talk about that in a few minutes, and you're going to do a few demos live. So if you happen to be in the chat because you're an LBS patron, please don't be shy and introduce yourself in the chat, and then you can ask questions to David. But before that, David, as usual, let's start with your origin story. Can you tell us what you're doing nowadays and how you ended up working on this?
Yeah, thanks. So, pretty much my whole uh, educational background is in econ. So, I did my bachelor and master's and PhD later on also all in econ, but always with a flavor of econometrics. So I was early on interested already in my undergraduate studies about statistical relationships. Particular back then, I was more interested in things like the relationship between debt relief, allocation, and then later on the country's development. So that involved a lot of what we call in econ panel data methods, which are really um, spatial type of models. And then during my graduate studies, I was then more interested in time series models. I really just loved kind of the simplicity and the mathematics of working through some discrete time series models. And that is, of course, then, widely applicable to many things in econ. And at some point, well, I got then really interested in thinking about how can you apply, higher dimensional time series models to problems where you have maybe lots of data. So especially like in finance and in macroeconomics, you have a lot of situations where you have very short time series, but potentially a lot of explanatory factors. Um, and so then classical methods tend to be fairly weak in terms of, well, one, power, but also then in terms of regularizing the variance sufficiently of the model to get useful predictions. So then I really delved into Bayesian econometrics with I suppose my first mentor, if you wouldn't call him that, Gary Coop at Strathclyde University in Scotland. So I did my graduate studies in Edinburgh, and then Gary Coop, was in Strathclyde, and I had the great honor of doing this Bayesian econometrics course with him. And it was probably the best 6 weeks of my academic life at that point. I just really loved his stuff. He has a great website, by the way, with a lot of resources if people are interested in Bayesian time series econometrics, some panel data stuff as well. A lot of multivariate stuff, in fact, so a lot of like vector order regressions, but maybe we can talk about that later too. And yeah, basically starting with the backgrounds that Gary gave, I delved further and further into Bayesian time series econometrics. And that's where I'm pretty much positioned still. So after that, I did my PhD also in Scotland, and there my sole focus was then on Bayesian methods for time series modeling, and then also some modeling in the direction of quantile regression as well.
Okay, interesting. Yeah, I didn't know you were econ heavy. That's interesting. That's a bit like Jesse Grabowski has a similar background. So I will refer people to episode 124, where Jesse talked about state space models. all of that. It's one of his specialties. So for background about that, we'll talk about that a bit today again. But for more background information on that, listeners, you can refer to that as a prerequisite, let's say, for this episode with David. And yeah, definitely, if you have a link to Gary Coop's like material, feel free to add that to the show notes, please, because I think it's going to be very interesting to people. At least to me. I love time series and vector autocracy stuff and so on. And Jesse and I are working a lot to make the PyMC state space module better and more useful to people. So yeah, if we can make all of that easier to use, that's going to be super helpful.
Oh yeah.
So yeah, awesome. Feel free to add that to the show notes. And thanks for this very quick introduction. That's perfect. That's a great segue to just start and dive in, basically, because you have a case study for us today, and you're going to share your screen. Maybe we can start with a quick theory of state space models, and mainly geared towards what you're gonna share with us today. So
Yeah.
you can take it over, David. Feel free to share a screen already or a bit later. Up to you.
Yeah. So perhaps before I go into the state space specifics, maybe I can first comment on like maybe what we're still working on today, and then I think that that will give you some background at least in why we're interested in still thinking about state spaces.
Yeah.
So because part of the reason why I entered the research realm around Alto was that Aki was working a lot on these kind of Bayesian workflow problems. So how to build models in various circumstances, how to robustly draw inference. And I mean, one thing that was, I think, direly missing from also the research I was doing at the beginning of my PhD was how to safely build out these time series models. Like um, how do you set priors on things that you can interpret, and then that allows you then oftentimes to add more complexity to the model without sacrificing in predictions, or at least statistics that involve predictions. And so one thing that we're working on at the moment, very in a focused sense, is this idea of predictively consistent priors, meaning that you start out with some notion of understanding about a statistic on the predictive space. That might be something like the R squared statistic. This measures the amount of variance fit. So this is a statistic between 0 and 1. Often it's bounded in that space for many models at least, and it measures the variance that the predictor term of your model is fitting. So let's say the location component of a normal linear regression over the total variance of the data. So the higher the R2 is, the better. So how much variance can I fit as a fraction between 0 and 1? And that kind of idea has been developed also in the Bayesian sense, where Aki and Andrew Gellman have worked out the kind of the methodology behind this Bayesian R squared, so Bayesian interpretation, which really is just a posterior predictive of the predictor term or the variance of your model over the entire predictive variance, including also the error term and so on and so forth. And what we recognize is that this statistic is well understood in many domains. So in econ, in the biomedical sphere, in a lot of social sciences, people usually have a model where they understand this notion of R2, this notion of variance fit. So that goes even beyond just the kind of classical normal linear regression case, but also for general GLMs. There are certain definitions of R squared that exist and people are able to interpret. And what we are doing in our group at the moment a lot, at least I'm working on it a lot, and with Noah also, we're looking into how can you set a prior on the R squared, and from that point of view, filter out the or define the priors in the rest of the model. So you start from a notion of understanding of R squared and perhaps some prior about this. And given this, how can you find priors of all the other components in the model?
I really love that. That's very interpretable, and that's also really how you would define models most of the time and think about them. Because if anybody who's worked with a model with an AR component in there knows that, and have done prior predictive checks, like these checks become crazy in magnitude if you have just an AR2. Like AR1 is fine with somewhat normal priors, but then if you have an AR2 component, and I encourage you, you can, like, if you use Stan or PyMC, go to the Stan or PyMC website, just copy paste the code for an AR model, and then just sample prior predictive samples from there with an AR2, and you'll see that if you use a normal 0-1 on the coefficients, the magnitude of the priors just becomes super huge with the time steps, and that's the big problem, and one of the problems that you are trying to address with the AR squared prior, and I think that's, the way you do it, I really love it because it's also very interpretable and intuitive.
Yeah. And then again, it's predictably consistent. So you have a notion of R squared, and if you generate from your model, so if you don't condition your data, you just do this push forward distribution where you sample from your prior, plug it into your model, generate predictions, then the prior predictive R squared will align with your prior expectations, or your prior knowledge of the uncertainty of R squared, let's say, in the shape of the distribution. And that's exactly what we're doing in this line of research for time series models, in particular stationary time series models.
Yeah. So thanks a lot for this background. I think that's indeed very, very important. And so now, do you wanna dive a bit more into the state space models and the case study you have for us today?
Yeah, let's do it.
Awesome. Let's go. So for people live in the recording, you'll be able to see David's screen, and otherwise, if you are watching on YouTube this episode, well, you also see that in the video. You'll see David's screen live. Otherwise, if you are listening to the episode, well, for that part of the episode, I encourage you to go on YouTube and check that out as soon as you can, because that's probably going to be a bit easier to follow.
All right, I'll just share my entire screen. I think that will be easiest.
Yes,
all right.
We are on. So
Nice.
This is the dynamic regression case study that you see on the screen. You have that, listeners, in the show notes of this episode. So the link is in there. It's on David's website. And now, David, you can take it away.
All right. So yeah, I think we covered some of the basics already with the R squared stuff. You can define this for AR type regressions and MA and ARMA type models. There are some special mathematical things you have to take into account for. So this time series structure implies a conditional variance, which you have to include in your prior definition. But here we're looking at something that's even one step further. So we go from a model that has as a target yt, this is a scalar. We relate it to a set of covariates. So those are the x's. They are here of dimension k times 1 per time point t. And we have this unknown regression vector beta t. So far, so good. This is basically the same almost as just your normal linear regression case, but indexed by time. The special thing about this model is that the coefficients themselves, the betas, they evolve according to a latent state process. So this is the second row in equation 1. This says that the coefficients vary across time according to an AR1 process. And this allows for the fact that the relationship between your covariates and your targets may change over time. So like a famous example in econ, for example, is that the response of interest rates that the central bank might set to do economic policy might change in response to inflation, which is one of the main drivers why policy changes over time, because maybe the target shift of this relationship, or there are some extra things happening like COVID, for example, which somehow distort this relationship for a little time. And this time varying process of how these coefficients evolve is then regulated, if you will, by an AR1 process. And in fact, those people who know time series, they will notice that since this beta vector is k times 1, you essentially have a vector autoregression here in the second line. But what we do in the paper for the simplicity of the math, and also what I do in this case study, is that I assume that this coefficient vector, which is called the state transition matrix, phi, just k by k, is diagonal. So it's only non-zero across the diagonal component.
Right.
What this means is that each
Yeah.
individual coefficient is only related to its own past individual coefficient, not other coefficients also.
Right. Okay. Yeah. And if it were not the case, would we be in the presence of a VAR model then? Vector autoregressive?
So it's still a VAR model. It's just assuming that all the other coefficients are unrelated, except for maybe this error term here. This kind of gives you some further way how to impose non-zero correlation between the coefficients.
Right. Yeah. Okay. So here we assume that the different. So we have k time series here that are modeled at the same time, right?
Right. So the target is still a scalar, but then the covariates are then k times 1,
Yes.
right? And then the process for the covariate coefficients, that is in a vector autoregression.
Right. Yeah. So the beta t's are modeled with the vector autoregression, but here we impose the correlation between the betas, the k betas, to be 0 when it's not when it's not on the diagonal.
Yes. Well, it's implied by the structure of the
Right.
state transition matrix.
Yeah. So that means the latent process is dependent only on the previous version of the covariate. The previous
Coefficients.
value of the covariate.
Yeah. Coefficients, yeah, exactly.
Yeah, and the k covariates don't interact, basically.
No, exactly. This
And-
keeps the math nice and contained.
Right, yeah. And so that means we have k latent states here, and we have k latent states because we have k covariates.
Yes.
Yeah.
Correct.
Okay. So
And you can...
yeah.
Sorry, go ahead. Oh,
No,
well, you can expand this in several ways. You can also, what we do in the paper as well, the AR2 paper, is that we allow also for time-varying intercepts. So you would have like another, let's say tau coefficient here, and then that could also have its own AR process. This would be then closer to this, what you mentioned before, Alex, this structural time series models, where you have multiple state processes modeled simultaneously.
Right. Yeah. So I think I mentioned that off the record. So I'm gonna.
Oh, sorry.
I'm gonna say it again on the record. Yeah. Basically, where here the idea would be to have like each latent state, so each of the k latent state being modeled with not only an autoregressive process as we have here, but maybe you have a local linear trend, and then you add to that an AR process to pick up the noise. Because the issue of just having the AR process is that when you are interested in out-of-sample predictions, is that the out-of-sample predictions of the AR are usually not very interesting because they pick up the noise. And so that's not really what you're interested in when you do out-of-sample predictions. So here, if you have a structural time series decomposition, you could be able to decompose basically the signal and the noise between these different processes. And so here, each of your k states would be modeled like that with one structural time series, but you would still have an emission. So like the YTs we see here, like the data usually in these literature are called emissions. And so your emission would still be 1D, right? Would still be a scalar emission.
That's correct.
Okay, cool.
You can extend that as well. So you
Right.
can make Y also multivariate. That's a different beast, and maybe we can talk about that later.
Yeah. These beasts start to be very big models where you have
Oh, yes.
covariation everywhere at the what is the? I always forget the name of the second equation. So you have the latent state equations, and the emission equation. Yeah, like the process equation and the emission equation.
Yeah.
Is that the right term?
Well, every literature has their own, how they name it. Like I've heard that as well, emission. I've never used it actually, to be honest. So in econ we call the y equation, this one, the observation equation, and we call this the state equation for the betas.
Right. Yeah. So I've seen emission and observation equation used interchangeably, and then the latent equation. So yeah, so that people have the nomenclature right and clear.
Yeah.
So, okay. Cool. So that's all clear, hopefully. So let's continue with the case study.
Right. And so one of the big problems here is that this unknown in the state equation. So the betas are explained by the past betas plus another error term. That's k-dimensional. This has a covariance, which we call big sigma subscript beta. And these, in this case, I'm also just making a diagonal structure just for simplicity of everything. They determine how wiggly the states are, because they inject noise in the state process, and the larger these variance terms are. So those are the diagonals across the error covariance term of the states. The larger these are, the more variable the state process is. And there's a huge literature on how to set priors for these, because if you let them be fairly wide, then what you'll find is that a horribly overfitting state space model, because you're essentially fitting all the noise in your data by making the state process as wiggly as possible. Oh, Alex, I think you're on mute.
Right. Sorry. Yeah, that makes sense. So basically, if you have too wide of a prior on the sigma from the latent state equation, and I think also I've seen in the literature this matrix, because it's often written also in matrix form, when you have, I hate the names of these matrix because they don't mean anything. I think it's like F and Q and H and R. It's like, I'm like, who invented these names? It's just, it's terrible. So
they try to make it as inaccessible as possible for newcomers.
It's completely stupid. So so you have in these matrix on the location of the normals, so F and H, usually in the literature they are called also the weights of the processes, and on the right, so the noise, I think they are called drifts also. There is a lot of different names for that, so that's why I get that out of the way for people right now. But basically here we're talking about the noise of the latent state equation. So this is the sigma beta in your case study, and people would probably see that also in the literature as the matrix Q. And so what you're saying is that if the priors on this matrix are too big, then basically your AR process will explain all the noise in your data, and your observational noise, so the sigma on the emission equation, so the observation equation, exactly, which is the sigma in your case study, which also people will see as I think R, the matrix R in the literature. Everybody knows R stands for noise, and so then that means this matrix will be really small. And if you just take that for granted, you would just interpret that as, oh, there is not a lot of noise in my observational process.
Mm-hmm. Yeah, correct. So this is the scalar, just to be clear. Yeah, exactly. And typically what the previous literature does is it says, let's put an inverse gamma. That's what I call IG here. Inverse gamma prior on the state innovation variances. So the diagonal of the state variance covariance. Let's put an inverse gamma on this and be fairly unreformative, or in quotation marks, something like an inverse gamma 0.1, 0.1. And I think the listeners of your podcast will probably immediately know, oh, this is a bad choice, because you have a very long tail and along the positive reals, and if your likelihood information is not very strong that identifies the variation of the states, then the prior will dominate, and you'll end up with a huge variance on your states, and therefore overfitting. And I can recommend this paper in particular. I'm hovering over it. In the case study, it's by Silvia Frischnatter, great econometrician and statistician, and her colleague Helga, who rewrite the state space process into its non-centered form, which allows you to put normal priors on the state standard deviation, which feature then in the observation equation. This might sound a bit esoteric without kind of seeing the math, but they go into much more detail as to why setting as an inverse gamma prior on the state variances is a bad idea. And we take kind of this idea one step further in that we say, okay, how about we start, in fact, from an R squared prior over the entire process, so something that explains the variation of this guy, so the state and covariate contribution over the variance of the entire data, because this is something that we often can interpret, say, like, oh, we know our model explains, let's say, 60% of the variation in our target. And then from a prior on this, what is the implied prior on the state variances? And just to be clear, what wide priors will entail, it will entail that the variance of this term, the predictor term in the observation equation, so x times beta, will dwarf the variance of the observation noise, which is, in this case, because it's just a normal model, this variance plus the variance of the observation model.
Yeah. So that's related to what we just talked about, and if that variance becomes too wide.
Exactly. Oftentimes you'll find that those overfitting models will in fact result in a R squared that is very close to 1. Basically saying that, oh, you're able to explain all of the variation in your data, and this is often highly unrealistic.
Yeah.
And particularly if you think about this with time series models where, and let's just briefly go back to the AR, so the simple autoregressive type model case, if you add more lags, so more information about the past, you wouldn't think that you can better predict the future, right? Oftentimes only the first couple of lags, or whatever the time series structure is good for prediction, and then if you increase the number of lags more and more, you wouldn't think that you're gonna fit more and more variance of future data, right? So in that sense, setting a reasonable prior on the R squared is actually a good thing also with time series. And this is kind of preempting some maybe screams that the audience has, like particularly those who are more trained in classical time series econometrics. They'll tell you, oh, R squared is not a good thing to look at for time series. And I agree when the model and data are non-stationary, because then the variance goes to infinity, and this R squared metric is not well defined. But in the case where you have stationary time series, the variance will be strictly below infinity, and therefore this R squared metric again makes sense to use.
Yeah.
Okay. But
Sounds a bit like, you could be R squared hacking with that, basically.
yeah, exactly. I mean, that's what people are afraid of with this R squared thing, right? Because they understand from their classical training, if you just include more and more covariates, then by definition, R squared is monotonically increasing with the amount of covariates you include.
Yeah.
However, in the probabilistic sense, you also have a probability distribution, a posterior probability distribution over your R squared, and here you can regularize with the prior away from this tendency.
Yeah, that makes sense.
And yeah, so if we think along the lines of what the R squared metric looks like, if we go through the math that we present in the paper, then we get this ugly looking fraction. And this is basically telling you that the R squared is a function of, let me zoom in a bit, is a function of the state variances, the state's AR coefficients, phi, and the observation noise. And what we've done to arrive here is that we integrated out the data, so the x's and the y's, but also the state realization itself. So you'll recognize that the betas don't appear here, but only the variance of the betas. Yeah. And the nice thing about this expression really is it's pretty much the total variance of your predictor term, so that's xt times beta t, over the variance of your predictor term plus 1.
Yeah.
And so if we wanted to set a certain prior, let's say a beta prior on this R squared metric, then we can figure out by change of variables what is the implied prior on the state variances on this kind of total variance term here.
Yeah. Yeah, and that's very cool because then you can just basically define that prior on R squared in your model, right? And then I guess just use that as the prior in, like, use that in the priors for the betas in the model directly.
Correct. Yeah.
Yeah. And so then, like, and I guess, and I think you give some recommendations in the paper, if I remember correctly, to set the priors on R squared, and then just basically do prior predictive checks to see that it makes sense in your case, and then go from there, and then you can fit your model.
Yeah, exactly. In the paper, we like to recommend this beta 1/3 and 3 prior. So parameterized here in terms of location and scale distribution. I think in PyMC you also have that coded up, right? The beta proportion. Yeah, exactly.
Yeah.
So that would be familiar in that case, because it has a lot of the mass towards an R squared below 0.5. Has a very gentle slope, so if the likelihood is pulling you in one direction, you're not going to overwhelm, most likely, the likelihood too much with an aggressive slope on the R square space. You're kind of weakly, let's say, regularizing toward lower R square spaces and therefore squared values, and therefore likely also overfitting.
Yeah. No, that's really cool. And so you're going to show a bit like now the implementation on different data sets, but also for people using PyMC, Austin Rochford did coded up basically that prior in PyMC on his blog. I linked to the blog post in the show notes. That's a very good blog post. So I definitely encourage you to check that out. His blog post though is limited to one part of your paper. You do more than that in the paper, and you'll get to that in a minute, David. But yeah, like that's a good introduction. I think in his blog post, Austin mainly, so he cuts up the prior and then generates data based on 3 different processes, different data generating processes, and then check that we can recover the parameters of the 3 different processes with the R-squared prior. You do that, but you also do more than that. So that's what we're also going to talk about today.
Exactly.
Yeah.
And so just, briefly walking through the machinery, then we are able to set the prior process, how it would look like in the Stan program. So we have then this variance term here in particular, which comes then from this whole R-squared machinery. And if you look very closely at these 2 equations, so one is this R-squared definition, and the other is the prior variance on the latent spaces, you'll see that here are 2 factors which, if they are included, they allow you to get rid of most of this very unwieldy looking stuff in the R-squared definition, and allows you then to isolate only the variance terms. But yeah, so there's more about this in the paper. I would encourage you, for those who want to dig more into this, to have a look at that. But the only other important thing I want to mention at this point is that you have another part of this R-squared prior that allows you to decompose the variance. And this you can think of as determining the importance of the individual model components and what they do mechanistically.
The different states, right?
Exactly.
Yeah.
And
so
what they do mechanistically is that they allocate the variance.
Right. Yeah. So basically, which states contributes more variance than another state.
Exactly.
Because basically, I think ultimately you can't really determine like the exact value of the variance that's contributed by each state. You can just in absolute. You can only do that in relative, right? So it's like the proportion of the variance is coming from that state, but you cannot really say it from an absolute perspective, I guess.
As in like marginal? Yeah, that would be hard. Yeah, that would be hard.
Yeah, exactly.
You can make statements about the entire variance of all the states.
Yeah.
And you can make a statement about relative variance in a way, and that's what this decomposition lets you do.
Yeah, exactly. Yeah, because I think if you want the absolute decomposition, that's just undetermined. So because an infinity of different decomposition of the variance of the different states will give you the same total variance. So yeah, I think like just the proportion is going to be identifiable, which is what this is doing. That's why you're doing a Dirichlet prior on this psi term.
Yeah, Dirichlet makes sense here because you're trying to find weights that allows you to decompose this variance, and then Dirichlet is just a natural prior of the simplex, really.
Yeah.
Mm-hmm. But yeah, I mean, you mentioned some things about identifiability. We're not taking hard stances on this. It can be a problem, I think, in state spaces more generally, like how can you identify where the variance comes from. But in general, I think putting a prior on the weight to decompose the variance makes sense. You want the data somehow to inform also that, I think.
Yes. No, for sure. Yeah. I mean, identifiability in general is hard for time series models. It's hard also if you use GPs on time series models. It's just that time series data is hard, and you don't have a lot of data in a way. You need a lot of covariates. Like if you can have external covariates, that helps a lot. But whether you're using state space models or GPs, I think GPs it's even harder because this is semi-parametric, whereas state spaces you have more structure by definition. But yeah, identifiability is always a big issue here, and the more informative data and priors you can have, the better.
And I'll mention that Arno Solin at Aalto has investigated the link between GPs and state spaces, and there's a very close computational link. Mm-hmm. You can find the posterior state space as if posterior of a GP as if it were a state space.
Right. Yeah.
You can think of also the state space as being somewhat of a discrete approximation to the continuous GP. You can also, because you also have let's say a variance of the GP in a way, or the latent function, in this case the state itself, competing with the variance of the observation model itself.
Yes. Yeah. And that definitely happens with GPs, right?
Yeah,
Because,
yeah.
like they can pick up, like they are so flexible that they can pick up the noise. Also, so you have to be very careful on the priors. And then also, and if you add categorical predictors to that, it's very hard because categorical predictors are not really predictors anyways. It's like, I find they don't really add a lot of information. They just, break down the model in different subsets. But you also need, like, if you can have continuous predictors indicate, like, informing the different subsets, that definitely helps. Because otherwise, the GP can fit anything, so it can definitely fit the noise in your different subset anyways. So,
Yeah.
But I'm not surprised that state space is generalized to GPs. Like, it seems to be a law of the universe. Everything is a GP in the end. I'm pretty sure that's what black holes are. They are just GPs inside.
Yeah.
So let's continue. I think you can now go to the application part of that, right? And you have an inflation forecasting example for us.
Exactly. And there are some other priors also in literature. So those who are familiar with econ might recognize this Minnesota prior. Those who generally follow also the shrinkage literature, they'll know the regularized Horseshoe prior. So we're incorporating these here too as a part of comparison. Yes, and then inflation forecasting. So here, some very crude code. I'm not particularly happy about it, but I think it does the job. It loads data from one of the feds in the US with this red-R package, and I'm just have a lot of functions here, so let me just skip that. Where the data are directly loaded from the St. Louis Fed website. I've changed it now locally to first download it and then upload it, because I find that these, like downloading from links, is not the safest thing to do. So here in this particular instance, what I'm showing is just then having first download the data and then uploading. And we have a set of 20 covariates. So 20 covariates, and then therefore also 20 states, because those are the regression coefficients which we allow to vary over time.
Okay, so I think that's interesting. Yeah, especially that plot here where you show the data. So you have the outcome variable is the inflation, right?
Correct.
And then you have 20 other time series, and each of these time series are a covariate, right?
Yeah, each of these time series are, so that's just the covariate value, the x's in the state space equation I was showing above. It's different data. It relates to financial market information. You have some sub parts of inflation in here as well. Industrial production, for those who in econ and macro, they'll know that industrial production is super important for explaining macro data movements. So that's included
and so
here.
That's like, if we look at just one of them, for instance, industrial production, that would be like for each year. I think it's monthly data, right?
Correct, monthly data.
Yeah, so it's like for each month, what is the value of the industrial production, whatever the value, the scale of it is. And so if you're looking at the screen, you have like these are lines, but basically these are just points, and like then each point gives you that value. And so for the corresponding value of the industrial production, you have a corresponding value at that same time point of the inflation, which is the outcome, which is the y of the equation, of the observation equations, and then the xt's are all the other variables, so 20 of them in total, which is k in the equations we saw before. So here, k equals 20, and so the matrix we talked about before, the phi matrix, that is also called the R matrix in the literature, the H matrix, sorry, in the literature, which is the matrix of the latent state process. Could be a full matrix, full rank matrix, but here it's only a diagonal matrix.
Correct.
And so the parameters in that matrix are called the betas. So, and betas are indexed by K and T. Is that all correct? Can we continue?
I think that was pretty much, yeah. Yeah.
Okay, cool.
Yeah. So, I think it's always a good point in the workflow to plot your data, just to know, is there maybe an outlier somewhere that looks fishy? You see, for example, here all the time series have usually like this S shape around COVID. This is 2020. So that there's a lot of funky things expected around this time.
Yeah, and I'm guessing you're scaling all the variables, standardizing all the variables before feeding that to the model, so that it's all the same scale.
So here I'm following the recommendations of the St. Louis Fed. They have a set of very good researchers who look at what is the best transformation for the data, given such that they are stationary, or weekly stationary at least. And generally, if you do econ analysis for macro time series data stuff, I would recommend just follow the recommendations of the statistical agencies, in this case the St. Louis Fed. So
interesting.
They will tell you what to do. Yeah, they are kind of the data authority on much of the US stuff.
Interesting.
Yeah.
Nice. So here, what do you do? Do you what is the recommendation? Are you doing any pre-treatment, or
I follow so they have codes. They mean different things. Like, let's say one-time difference, maybe growth rate calculation, maybe you leave it entirely unprepared. So it depends on the time series. Okay. Exactly.
Interesting. Yeah, because these time series have very different scales. So
exactly.
That's definitely something I would be concerned with, especially when you give that to HMC. So yeah.
And so the R-square prior, in fact, can be made robust to the scale of the data by including the variance of your covariate information in the prior itself.
Okay.
So you kind of scale appropriately.
Which is not done here, right? I've not seen that in the equation.
Let me see. I think for simplicity, I
think you.
For simplicity, I said, or I assumed that the covariates all have variance 1, but in the model it would be then another fraction here, divided by the variance of x. But more on that also in the paper, so that's where we have that more. Okay. So now we know what the data are looking like. So just to motivate where time variation in the coefficients comes from, what I've done here is that every 100 months, starting from 1980, I do a simple linear regression where I take a univariate regression, so just our target inflation against, let's say, industrial production, save the coefficient value, and roll until the end of my data availability. And what we would find, if there's indeed variation in the coefficients, is that we also find variation here.
And so that means basically you run a univariate regression for each time point individually?
Exactly.
Like in a for loop?
Exactly. That's exactly what this guy is doing.
Okay, so the model doesn't know anything about time correlation. Or it's you just run 1990 against 1990, then 91 against 91 again, and blah, blah, blah. Okay, yeah.
I mean, it's not a statistical guarantee. However, if you would find that those lines are all just straight, then you probably are not going to find much variation, even if you do all the bells and whistles that we offer,
Yeah, no, I mean, and that's a good check, right? Because these models are not. The models we're talking about here are not trivial. Each time you need to do state spaces or Gaussian processes or all, it's not trivial. So if you don't have time variation in your data, that's better. Honestly, your life is gonna be easier. If it's that's interesting. I didn't know about that method. It's it's a good heuristic, right? It's just you can just take a subset of your data, maybe you randomly sample, or you just take every I don't know, 5 or 6 months, and then you run a regression in a for loop in that. I mean, not even a for loop, you just vectorize that with standard prime C, but it's just it's an independent univariate regression, just plain. You could do that in PRMS or BEMBI even. And then
exactly.
If the regression coefficients come up very, very close to each other, then that probably means you don't have that much time variation.
Exactly.
Here it's not
That's
the case.
also
Here we can see the lines are very, very wiggly. So
exactly. It's also part of the workflow. I think you should always start simple. Always start
Yeah.
with a simple model. See if you can find interesting relationships. You can even start just by, you do a ggplot and then you just have put an LM between the data points in there and just see, oh, is there any kind of interesting dynamics you could pick up? And this is doing this essentially 20 times.
Yeah. I would probably, for that plot, that'd probably be useful if you shared the y scale, the y-axis between the plots, because like they have different scales, and so probably that will also inform about which cohorts seem to be more variable in time than others.
Yeah, that's a good point. I think for some you can already see that there's some significant variation, like let's say industrial production. I think like if you look at the scale of the data before, it was between I think 0 and 15. The coefficient goes between 0.2 and minus 0.4. So there's some variation to be expected.
Nice.
All right.
So now stand models.
Yeah, so I've hid them below, so you can look at them. I think when you have the time. There also we have a repo for the paper as well. There we have written a SnakeMake pipeline, so it's maybe a little bit obscure if you haven't gone through SnakeMake pipelines before. But the stand code is also there, and here I reproduced it for the dynamic regression, so the state space model that we're looking at here. That's at the end of this.
Yeah, and I've put that link in the show notes, of course.
All right. And so here we're just setting up the models and sampling from them. I've coded up one indicator there that indicates whether it's a prior predictive or full posterior analysis. So basically including the model in the model block, or the likelihood contribution model block or not. And we were talking in the beginning about what happens if you have fairly unrestricted priors on the variances of your coefficients in your model. And this is exactly what I'm showing here. So the Minnesota and RHS, those are two popular shrinkage priors for time series. If you sample from the priors, plug it into the observation equation, generate what would be the prior predictive y's, and then calculate the R-squared statistic, you'll find that these two models say a priori we expect to fit 100% of the data variation. Whereas if we you look at our model, the AR2, here we have full control about how this distribution looks like, and this is approximately this beta 1/3 distribution. There's also a nice way to check that your coding is correct. Like if this had a entirely different form, like a 10 structure around 0.5, then you would also know, okay, something's wrong with my code.
Yeah, for sure. And that's really why, that's what we were talking about before at the beginning. Like that's what I really like about the way of setting prior that way. Also, that's how you can see that setting your priors with other priors than the IRR squared is really weird. Because before seeing any data, you're telling the model to expect to be able to explain all the variance in the data with your latent state equation. So it's like saying, oh yeah, there is no noise in the data at all. It's possible, but I would bet it is very, very improbable.
Well, there can still be noise in data, but just it is dwarfed by the variance of your
the latent space process. Yeah, it's going to pick up everything, and I don't think it's a good modeling choice. I think the error squared process here in the prior distribution makes much more sense.
Yeah. And if you know inflation, or if you know kind of your inflation data in the US, you also know that it's a really hard time series to predict. So there's a whole literature about how hard it is to predict inflation. And we would expect, in fact, lower R-squared, something between 0 and 0.5. Like if you're a specialist in econ, you would say, okay, 1, not possible.
Yeah.
All right, and so here I'm just generating still from the prior. So just to motivate what the variance looks like of the coefficients to each of these time series, I just sample from the state process. This is how it looks like for the AR2. It's not informed by the data, so they all look approximately like a, distributed around zero. And this is how it looks like for the Minnesota and the RHS. And you're still plugging in the X information. You're not informing the prior with a likelihood at this point. But you see that the variance of the data also heavily influences the
Yeah.
prior predictives here.
And so these are the betas, right?
Yes, right. Yeah.
Yeah, and you can see, like, definitely if you see the screen here, people, or if you're following up with a blog post, these are weird. These are weird prior checks. So yeah.
Yeah. You wouldn't expect your coefficient value for a certain time series to range between -50 and 50 if your range was like between 0 and 100, let's say, for your target.
Yeah, and also
Yeah.
because that implies that then other time series have zero contribution, and you cannot really control also which one have zero. So also that's also it's quite bad. It puts a lot. Basically, also the problem with that is that it puts a lot of onus on the data to be very informative, and
Yes.
that might not be the case, especially with time series data where all these models have a lot of parameters, and so that's already a big responsibility for the model. But then if you like put even less prior information in there, that means you need to squeeze even more information from the data, where the data already in time series is not necessarily the most informative. So it's like that's piling up on the complexities.
Yes, correct. And good point, by the way. I think also for listeners, you can have very fancy priors and everything, but if your likelihood is very, very strongly informative about the value of parameters, it oftentimes doesn't matter so much what you're doing with the prior. So it can happen that the data information is fully overwhelms the prior. As you just said, you have k states, you have t time points. That means you have k times t parameters you're estimating. That's a lot.
At least, and that's just the badass. But then you can,
Yeah.
like, if you start sharing information and so on, you add parameters to be able to do that partial pooling and so on. So, and also like each time that means also like you subset the posterior space if you want in a way, and so that means that each part of each subspace is only informed by one layer of the data. So it's not like you're taking the full time series and then you're just sharing everything. It's no, like then you have that time state and these state, and that's just like you might end up just having one data point to inform that parameter in the end. So
If at all. Yeah.
Yeah, if at all, exactly.
Yeah. So priors matter. and these
Yes,
state
exactly.
spaces.
Especially for a time series model. And it's like, yeah, that's basically my point, because also I've discovered that with experience, right? It's like, and that's why if you don't see any time variation, it's way better, because then if you ignore time, you basically can pool of your data and aggregate it, and so that increases your sample size, basically, and so that increases the information that you have in the likelihood and decreases the information of the importance of the priors.
Yeah, exactly. And of course, the nice thing about this R-squared stuff is that you're a priori saying that those states, they have to fight each other for the same variance. Like we have
Right.
upper bounded the variance, so they have to fight each other for explaining the data, in loosely speaking. So if one state is important, let's say that means away from zero significantly in some sense, then another state has to give, like it has to then have less variation.
Yeah, and that comes from the Dirichlet prior.
Yes, correct. Yeah, and
Yeah,
this
so
manifests.
here now we have the posterior distributions on the R squared. We can see that they get like we have posterior shrinkage, so that's really good. They all go in the same direction, but it's just that Minnesota and Hofstra prior were so biased towards the one, the priority, a probability mass geared and biased towards an R squared of 1, that like it is super hard for them to get away from it too much, whereas the error squared prior is much more aggressive on saying that the latent states are not picking up too much of the noise.
Yeah, correct. And maybe this, I don't know if this is a good value of R squared. I'm not making a statement about this, but there's a big difference, and that's what's important. And we can verify whether this is good or not later with predictions.
Yes. Yeah. And so basically what the R squared model here is saying is that the covariates in here, the latent states, inform much less of the variation in the data than what you would conclude if you're using Minnesota or RHS priors.
Mm-hmm. Yeah, absolutely correct. Yeah, nothing to add. Very good. Thanks.
Awesome. Let's go on.
You can also think in time series about like some notion of R squared over time, and this literally takes just the contribution of the states and covariates in terms of the variability per time point, and relates it to the total variability per time point. And this is like how much of the variance of the data can you explain at each individual time point. And what those posterior series are saying here is that the Minnesota and RHS, which tended to have a marginal R squared, so total over all time points, to be larger, also show much more variability over time in R squared.
Okay, yeah, that's interesting. And you have like that formula. I guess you implemented it in R in the package somewhere.
Yeah, well, I've just coded it myself here. I made a function that's up below, and I just call it. So this is the extract R2 function. But it's very easy. You really just take a sample from your posterior, those beta. You multiply it by the inner product of the. There's a mistake with transposes, by the way. I'll fix that. You multiply the inner product of the covariate vector per time point, and relate this to that quantity again and the observation noise. Yeah, this is like a way how you can think about R squared over time.
Yeah, it's definitely something that's like, needs to be, if you're using a package to that, like let's say we have that in PyMC state space, that's a function we'd like to have, basically.
And same story, more variation with Minnesota and RHS compared to AR2. And then here are now the posteriors of the beta vector over time. So we have drawn our MCMC samples, we take the average over the MCMC samples, and then just look at the time series of the beta states. And so we see some variation with the AR2 that's being picked up. There's a lot of variation for all the time series in a way, very similar scale. So nothing is like fully dominating the variance.
So these are the betas. Like these are the weights of the latent states.
Exactly. And for those who are following along, TVP in those graphs refers to time varying parameters. In econ, we refer to these state space models where you have a state for the coefficients for in a regression. We call those time varying parameters for whatever reason. I mean, it's I understand the reason, but it's a little bit too general. And this is what happens with the Minnesota and RHS, the same picture basically. A lot of the series get shrunk to zero, and then a couple time series have a lot of variation. Just to show you this how it looks like for RHS too.
And actually, that a quick question that's a bit more theoretical, and I don't know if you'll be able to answer, but what I'm wondering, maybe what I'm a bit confused by here is that a state space model with discrete or continuous latent spaces here?
Discrete.
Yeah, okay.
Yeah, discrete.
but they are not mutually exclusive.
No, I mean a
Just because
discrete
so
is a
in
subset of the continuous time series.
right, yeah. But it's not. So it's not an HMM. It's not a hidden Markov model, is it?
Well, it depends how you define hidden Markov model in a way. So
Yeah.
if you say that the hidden or the Markovian process here is this this discrete state space transition, then it would be, but it's not in the sense of what you sometimes see, where you say, okay, we have 5 discrete states for a coefficient, and we draw inference onto the location and magnitude of where the states are.
Right. Yeah, for me, an HMM is more like that, where it's like we have discrete states, but you're switching from one state to the other, where it's like, let's say you have 5 states, at some part in the time series, the regime you're at that dictates your emissions depends on, well, an AR process, for instance, that belongs to state 1. And then at some point, the regime switches to state 2, and then it switches back to 1, or goes to 3 or 5, etc.
Yeah.
That's more like that, where it's like, that's why I was saying mutually exclusive. Whereas here, the states are not mutually exclusive, like literally, because the parameters, in the sense that the parameters can be all active at the same time. Like you can have beta 1 positive for industrial production, and also beta 1 positive or negative for AAA FFME here, which I don't know what that means, right? It's like all the states can be active at the same time. And it's like, and then the aggregation of them gives you the emissions, which in my mind is not really a hidden Markov model, but it's more like kind of a discretized linear Gaussian state space.
Yes, and well, okay. I mean, the hidden Markov model can also be discrete, right? But then, what's not the case here is that, let's say you have 10 time points, and you have 10 beta states, then it cannot be beta 1, beta 2, beta 3, beta 1. Like you're not repeating the same states along the time series. Every new time point implies a new state. They can be related, but there's no transition matrix which says that there's a probability of going back to beta 1 after time point 1 has passed.
Yes. Yeah. So that's why it's really different in my mind. Like that looks much more like a linear Gaussian state space model to me, whereas the hidden Markov model is more something like a categorical, not necessarily emissions, but categorical state, at least.
Yeah, I mean, they're in some way related. I think the Hamilton time series book has some nice description on the relationship between these models. I read it during the beginning of my PhD. Don't quiz me on the details, but it's a cool read if you want to like learn more about that stuff too.
Mm-hmm. Yeah. I mean, I'm sure I'm confusing some people here, but it's because I'm confused myself on that. So like I'm still trying to understand really the difference. I know it's a nuanced difference, and that maybe doesn't really matter. But yeah, it's just like for me to understand really what the actual difference is. But
I mean,
okay.
Just to recap, we're not drawing inference on another transition matrix which tells you the probability of going between states. It's just that you start at a state and you end at a state, and what happens in between can be fairly unrestricted.
Yeah. It's more like so here each case state is like one-dimensional, so it's like tracking the position of a particle, for instance. Like that's what each state is doing, where we're tracking the position of the inflation particle in the subset of industrial production, for instance.
Yeah, correct. Mm-hmm. And yeah, pretty much that's what's going on here. Just to recap, a lot more variation in some states than in others compared to the AR2, which has like more like a constant, almost variance across all states. And you might ask, okay, well, which one is better for prediction? And it turns out that the AR2 is then significantly better in terms of ELPD diff.
Yeah, which is great.
Yeah.
You were happy to see that.
Yeah, exactly.
Awesome. Yeah. Maybe a last question related to that. So I linked to Austin's blog post. Can you tell us basically what the difference between what Austin is implementing in the blog post and what you're doing in the paper is? Because Austin's just doing one part. That blog post is just implementing one part of what you're doing in the paper. So can you make sure that is clear to people what the difference is?
Yeah, of course. Thank you. So the main difference is that Austin is looking only at one of, or a subset of the time series models that we defined this R2 prior over. So in the paper we have AR models, MA models, ARMAs. We have AR plus X, so independent covariates included with the AR regression, and we have some simple state space models. And what Austin did was he took a subset of only the AR simulations and looked at the recovery for the true parameter values that he sets according to also what we do in the paper with the AR prior set over the AR coefficients.
Right.
So there's no unknown states. It's all just y the target, and then on the right-hand side of the equation you have lags of your target.
Yeah, because then it's just like y is the likelihood of y is an AR. So that's all.
The model is AR, and then the likelihood is conditionally normal. Yeah.
Whereas something that is more practical is what we were talking about at the beginning, where you would have y as a normal emission here, as you have in the case study, but then the states could, well, not the state, but the observation equation could depend on each state being a structurally decomposed time series with an AR process. So local linear trend plus AR, and you will use the AR squared prior on the AR coefficient.
Yes. Well, I mean, in the state space models, we don't actually, the AR to prior is not set on the state space AR coefficients, but on the state space's variances.
Okay.
Because that is the main determinant for the variability.
Right. Okay. So the how did you call that here in your case study? The sigmas. So in the literature I know about, it's the R matrix. So the variance of the state equation, and here you called that the sigma.
Capital sigma underscore beta. Yeah.
Sigma betas. Okay. Yeah.
Yes, exactly.
Okay. Cool. Awesome. Great. So thank you so much, David, for that in-depth case study. Damn, that was good, and I think that was a first on the show. So thank you so much for doing that. And you listeners, let me know what you thought about that. I really like that kind of hybrid format content. I think it's more hands-on, and I think it's very practical. That means you guys have to check out the YouTube channel maybe a bit more, but I'm fine with that. So yeah, that was at least super cool to do. So thank you so much for that, David. I think you can stop sharing your screen now, and I've already taken a lot of your time, so I still have a lot of questions for you, but I'm gonna start playing us out because I know it's getting late for you. But maybe what I'm curious about is maybe for your future work. Like, what do you see as the most exciting trends or advancements in your field? and also where do you see the future of probabilistic programming heading? Because of course you work a lot on Stan. You also work on some Python now, thanks to Osvaldo being there with you. Like spreading the dark energy of the Python world. Thanks, Osvaldo. So basically, I'm curious to know where your head is at here, where your future projects are.
Mm-hmm. Yeah, I think there's a lot that excites me about our research agenda at Alto, but also others. What excites me in our group is that, and the people that we work with more generally, is that we're still very actively thinking about how can we set priors about things that we have expert knowledge on. Summary statistics, something about the predictive space, and what do these prior imply then for all of these coefficients that we have in the model, where we typically just go ahead and set normal 0-1 priors, that is still under active development. So we have like let's say the simple time series stuff covered to some degree, but there's so much more to be done in time series, even with multivariate models. So there are ways to define this R-squared stuff also for multivariate time series stuff. I think that's really cool and has a lot of policy applications as well. Because central banks and so on who do the econ policy for a country, they often know that everything is related to each other.
Mm-hmm.
If you're modeling inflation, you're also going to model GDP and so on and so forth. And doing this jointly is really the way to go in the end. And these priors, I think, can also be very good for those kind of questions.
Mm-hmm. Mm-hmm. Yeah.
And
no, for sure. Like in the end, kind of everything is a vector autoregressive model.
I mean, you're preaching to the choir, but I would tend to agree, like at least approximately.
Yeah. I mean, like if you basically, but often the limitation is the computational bottleneck, right? But honestly, almost all the time you would want vector autoregressive processes on the observation equation and on the latent state equations. Like most of the time, you have correlations everywhere, and you wanna estimate that. The problem is that we often don't do that because it's just impossible to fit. But ideally, would be able to do that.
Yeah, exactly. And a lot to be done there still. And we're also looking a lot into still. Workflow in terms of how, prior is one thing, but a whole new aspect also is model selection. So we're also very excited about a project where we're investigating the question of when is selection necessary if you have different priors to fulfill your goal in terms of prediction in the first case scenario. But even for causal analysis, this is an important question. How do you set the priors, and do you need selection to somehow produce reasonable predictions for the treated versus non-treated? And when you have lots of covariates or other structure in your model, so we're working also on that. I think there's going to be fun results going to come out of that.
What do you mean by selection here? Selection processes, selection bias, or?
More like a variable selection or like component selection. Okay. Yeah, so
right.
There's some stuff like this predictive inference, which does selection based on can you find a surrogate model which gets as close as possible to a full model, like a Gaussian process that is hard to compute. And like statistical folklore tells you that if things get too hard, as in you have too many components, do selection. Because then you implicitly decrease the variance of your predictions because you're focusing only on a couple things of your model. And what we're kind of saying is, that's not necessarily true if you have good priors. And understanding when that statement in fact is true and when it is not so true is an interesting question, because let's say in those causal analyses where you have randomized controlled trials, let's say a drug is being administered to one population randomly or not, then does it make sense to let's say use an R-squared prior, which implicitly will say the treatment effect is correlated with other parameters that you're estimating, and is that a good choice? And you know, what we're saying is like it depends, and we kind of go into detail about when R-square priors and priors like that are good, and when they're bad, and when selection is needed and when not.
Nice, yeah, yeah, super interesting. Let me know when you have something out on that. I'll be very interested to read about that and maybe talk to you again about that, because that sounds very very important and interesting. So yeah. I'll be very curious about that.
Maybe one thing about other people's work, I was very selfish talking about our work, but I think there's some really cool stuff I'm excited about that comes out from groups around like Paul Berkner and so on, which are also picking up work on normalizing flows and amortized Bayesian inference. I think that stuff is going to be really good going forward, because you can simplify computations, you can reuse models for huge estimation tasks. I think this will make the kind of general Bayesian computational workflow much more easier in the future. So I think kind of using this, maybe integrating it with like the knowledge that we're working on, also how to model, and then how to do computation. Those things, they're interdependent. And I think for the future, I'll be very excited to see what comes out of that.
Yeah, completely agree with that. And I'll refer listeners to episode 107 with Marvin Schmidt about amortized Bayesian inference. That was super interesting, and haven't been able to use that in production yet, but really I'm looking forward to be able to do that and like have an excuse and a use case for that, because this looks really cool. And yeah, I completely agree with you that it has a lot of potential for that. And yeah, everything Marvin and the Baseflow team and Paul Berkner are doing on that front, and like even anything Paul is doing is just like always super brilliant and interesting. And what I love is very practical. It's not research that's like, okay, that's cool, but I can't even do that because the math is too complicated and it's not implemented anywhere. That's always his research, and you guys' research at Alto is what I really like. Is like it's always geared towards practical application and not just, okay, that's cool math, but nobody knows how to implement that. So that's really cool, and well done on that. I think it's amazing. And talking about normalizing flows, I'll also add to the show notes NutPy from Adrian Zaybolt. So he was also on the podcast. I will also link to his podcast episode with me, where he came and talked about zero-sum normal and NutPy, which is an implementation of HMC, but in Rust, so that's much faster. And now he did something very cool in NutPy, and you can use that with PyMC and Stan, models. But now you can use normalizing flows to adapt HMC in NutPy. So basically what this will do is first run normalizing flow and train a neural network with that, and then once it learns the way to basically turn the posterior space into a standard normal, then it will use that to initialize HMC and run HMC in your model. And so, of course, you don't want to do that on a simple linear regression, right? It's just overkill, because it's going to take like at least 10 minutes to fit, because you have to train a neural network first to learn the transformation of the posterior space that would make it a standard normal. But if you have very complex models with very complex posterior space, so things like Niels funnels, banana shapes and so on, where it's very hard to find a reparameterization that's efficient, then trying the normalizing flow adaptation of NutPy could be very interesting to you. And literally, if that works in your case, it can make your MCMC sampling much faster and also much more efficient. So that means much bigger effective sample size. So I will definitely link to that in the show notes, because I think it's something people need to know about, and we'll try it out, and that way Adrian can know can know this is working out there in the world, and I know he loves that. So, awesome. Well, David, that's cool. Anything you want to add that maybe I didn't ask you or mention before I ask you the last two questions?
I don't know. I mean, I think we covered a lot of ground here. I think there's a lot of cool stuff here. It's probably impossible to find it all. I do want to make an honorable mention to all this work that goes into prior elicitation. I know that you're also interested in that, Alex. But there's also work that is coming out of Helsinki and Aalto, which is looking into how can we go from knowledge about effects of covariates to priors. And we have tools that can go for work for simple cases very well. But what if you have correlated effects, like let's say, I don't know, age and income predicting, I don't know, school outcomes or whatever, right? Those things are often highly correlated, and then going from like a conditional expectation on predictions to the prior. So let's say you have this age and this income. What does that? How does that relate to education outcomes? And specifying the prior in that way, I think, is super interesting. And there's a lot of cool stuff also being developed that helps to specify these priors with then artificial intelligence, like AI trying to kind of go from a very prose and conversational way of talking about then what we want to do a prior on to then actually implementing it in things like Stan and PyMC and so on. I think that's a lot of the future that's awaiting people who are maybe not so interested in learning Stan and details, but still want to do cool Bayesian inference, and then these kinds of things I think will make it accessible to a much wider audience than it is right now.
Yeah. I mean, definitely. I mean, even for us, who are like power users of the software, that would make my model workflow be way faster, because most of the time that's a much more interpretable and intuitive way of defining the priors than trying to understand what the prior on the AR squared process of my time series of my structural time series model is going to mean. Like, the only way I can understand what this means right now is just doing a cumbersome iterative process of changing one knot at a time and seeing how that impacts the prior predictive checks and maybe an interesting metric, like the prior squared or something like that. But like, that's the only thing that's really reliable right now, and it feels like it can be automated for sure. Because it's like a lot of cumbersome back and forth, basically, where probably something AI assisted would make faster.
Yeah. But still, it's kind of nice that you still have to get your hands dirty in a way. Like, not everything is too automated, because it does let you learn a lot. But the problem still remains that not everybody has the time, inclination, or interest in getting their hands that dirty.
Yeah. No, and also, like, everything has a trade-off, right? So the time you spend on that is not time you're spending thinking about expanding your model, making it more expressive, and so on. So if we can make that easier, that'd definitely be amazing and a high impact. Awesome. So I need to let you go, David. That's already like 1 hour and a half we're recording, so I don't want to take too much of your time. You'll come back on the show for future work you have, for sure. But before you go, let me ask you the last two questions I ask every guest at the end of the show. So if you had unlimited time and resources, which problem would you try to solve?
This is a really weighty question, and I feel like there have been such good answers in the past. So it's really hard, I find, to add to any of that. But let's say that with infinite resources and everything, I've done all the things that we should do for humanity, right? So we've been the good guy already. I think what I would do is I would go back to one of those core econ things that are important, namely how do you set policy such that you maximize the utility of a nation or maybe all nations? And one particular question in econ is how can you achieve the best amount of good or the most amount of good for all people? And this is a really difficult question because there are always so many trade-offs in policy making. You do one thing, you improve the life for others, you decrease the benefit for another group. And I think if I had infinite resources, I would try to find the optimal policy rule that would satisfy the condition of best amount of welfare, whatever that definition is, by the way. I guess that needs to be conditioned on philosophy, across all time periods. And then basically have a fairly automated rule that kind of is running in whenever any economic actor takes any decision. And what would happen, that would be that you would basically have like a steady state process for the entire nation's economy without any significant variation. So like policy making would always be such that we would all have kind of the best economic life possible within the confines of the chosen philosophy and the constraints of resources.
That's fine. Yeah, I love that. Very nerdy answer, and I really appreciate that. Thank you. I appreciate the effort. I love that, and I definitely resonate with that. Although I would argue we're very far from that, so you would need to do a lot of work. Good thing you have unlimited time. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
So again, dead is like too much of a weighty question, so I'm just gonna sidestep that. I think there are too many cool people that I would like to talk to. But I think who is alive and I would really like to have a dinner with is Chris Sims. He's a Nobel laureate in econ. He, in fact, was one of the initial researchers on vector autoregressions, Alex. So if you're looking into vector autoregressive stuff, then Chris Sims is like one of those OG researchers in a way. And he won a Nobel Prize on related work related to more policy-related stuff. But he's done a lot of really interesting time series econometrics, and I would love to just have a conversation with him over dinner where we talk about how can we integrate, let's say, the work on R-squared stuff and safe Bayesian model building with his time series knowledge. I think that would be such a cool thing to do. And in fact, he I think did a lecture recently in the past maybe 2 or 3 years where he was suggesting that people should look at econ problems with multiple lenses. This goes a little bit into this kind of multiverse idea of statistical modeling and acknowledging that there's a workflow that you have to work through. There's not always one solution for every statistical problem in econ, which is kind of dogma, I think working with him on that would be such a cool thing to do.
Yeah, definitely. And I've never had a Nobel Prize laureate on the show. I've had a sir, but I've never had a Nobel Prize laureate. So yeah, like if anybody knows, Chris, right?
Chris Sims, yeah.
Yeah. Then like let me know. Put me in contact. I'll definitely get him. Try and get him on the show for sure. Amazing. Well, David, thank you so much. That was awesome. Really had a blast. Learned a lot, but I'm not surprised by that. I had a good prior on that, and thank you so much for taking the time. Please let me know, listeners, how you find that new hybrid format. I really like it so far. So unless you tell me, oh, I really hate it, and most of you tell me that, I think I'll keep going with that whenever I can. So, as usual, I'll put a lot of things in the show notes, for those who want to dig deeper, David, so your socials, your work, and so on, for people who want to dig deeper. And thanks again for taking the time and being on this show.
Oh, thank you.
This This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after